So we have seen all these things earlier in the biophysical chemistry. What are acids? What are bases? And what is a conjugate acid-base pair? And what is an amphoteric solution? And why do you say certain electrolytes are strong and certain electrolytes are weak? And also we have derived the equation for Anderson and Hasselbalch, by which the pH of a buffer can be found out. And also, what is a buffer? What is buffer capacity? And the actual concentration of a solvent acid and the salt to acid concentration ratio, how do they affect the buffer? All that we have seen. And also we have did 3 case studies to understand which combination will be a better buffer, and also normal range of the buffers, and also some precautionary measurements about the buffer. And today we are going to discuss the strength and the concentration of an acid. See, strength of an acid is spoken in terms of H plus ions. Suppose if the acid solution is more concentrated, then the ionic atmosphere will resist the motion of the ions. Before that, you should understand what is ionic atmosphere. Suppose I take a sodium chloride solution, the Na plus ions. If Na plus ion is considered the central ion, then that will be surrounded by Cl minus ions. Cl minus ions will surround the Na plus ion, and it will be like a ball shape, where at the center Na plus ion is there, which is surrounded in all directions. In a 3-dimensional view, you can look it as a ball, where the ball, it is the center point is surrounded by the Cl minus ions. That Cl minus ions altogether is called the ionic atmosphere. Similarly, every Cl minus ion will be surrounded by the sodium plus ion. So every sodium plus ion will be surrounded by the Cl minus ion. Every Cl minus ion will be surrounded by the sodium plus ion. So this is called ionic atmosphere. If this ionic atmosphere becomes very thick, then what will happen? The sodium plus ion will start moving towards the cathode in an electric environment, but the sodium plus ion will be dragged, or a negative acceleration will be given by the ionic atmosphere. So when the acid solution is more concentrated, the ionic atmosphere will restrict the motion of the ions. Therefore, the actual protons which are active will be very less. So that is why we are introducing a new term called effective concentration. What is the actual concentration? What is the effective concentration? So effective concentration is always less than the absolute concentration because of so many factors such as ionic atmosphere and other things. So concentration is the actual quantity of the acid taken, but strength is the activity of the H plus ions. So the concentration can be taken as effective concentration and absolute concentration. Effective concentration is mentioned as A, and absolute concentration is a C. But strength, we are speaking about the activity of the H plus ions. How much of H plus ions are ready for the reaction? That speaks about the strength of the acid. So for very dilute solutions, activity is equal to concentration. They are equal for dilute solutions. But when the concentration increases, activity is equal to gamma C, where gamma is called activity coefficient. Therefore, concentration and strength, they are different in their definitions. Concentration is actual activity, actual quantity of the acid taken, but strength is in the actual quantity of the acids, how much of H plus ions are actively participating in the reaction. That is the strength. So you should understand the difference. Suppose I am doing the titration. When I do the titration, suppose I take a hydrochloric acid, which is a strong acid, where the H plus ions are always ready for the reaction with the OH minus ion. Therefore, the neutralization spontaneously takes place because the H plus, the HCl molecules are existing in the solution in the form of ions. They are completely ionized. But if you take acetic acid molecule, which is a weak electrolyte, only less amount of H plus ions are available for the reaction with the OH minus ion. Therefore, what happens when OH minus ions from the NaOH, they combine with the H plus ions which are generated from the water. You should carefully look into this sentence. Actually, the H plus ions from the water combine with the OH minus ions to form water molecules. In order to attain the equilibrium, now the H plus ions are to be supplied to the water molecules. Therefore, all the time just 1.3% of acetic acid molecule, they are remaining in the solution in the ionized form. See, suppose I take some 100 molecules of acetic acid. Only 1.3 molecules are ionized. So when the H plus ions from the water are consumed, then another 1.3% of the acetic acid gets dissociated and increases the H plus ion concentration, and hence the equilibrium is maintained. Then when the reaction is complete for the supply of NaOH from the burette, then one more 1.3% of the acetic acid gets dissociated and the H plus ions maintain the pH. Sorry, they will maintain the equilibrium. So the, oh, just a minute, wait, I will be back now. So when you are doing the titration, actually what happens is a sodium hydroxide solution is coming from the burette to the beaker or the conical flask where the acid is taken. If it is a strong electrolyte, the H plus ions are readily available. So whenever a OH minus ion comes down, immediately the H plus ion which is already existing in the solution will react to form the salt and the water. But in the case of weak electrolyte, when the titration proceeds, then only new weak electrolyte is getting ionized. So initially just 1.3% of the acetic acid molecules remain ionized. So once the H plus ions are consumed, then again 1.3% gets ionized. That is why the titration profile of strong acid or weak acid versus a strong base almost remains the same. So similar titration profile for both the strong acid and weak acid is observed because the ionization continues as the titration continues. In the case of strong electrolyte, ionization is almost complete, but the titration continues. Therefore, the titration profile is similar for both the strong acids and weak acids. But the acidity measured by titration, I am just titrating to find out the quantity of the H plus ions. That is the acidity of an acid. The acidity of an acid titrated, measured by titration, it is called total or titrable acidity of the solution, or it is called concentration of the solution, but this is not the strength or actual acidity of the solution. You should understand this point. So by titration, what you are finding out is the total acidity. It is also called titrable acidity, or it is also called concentration of the acid solution. But what you are finding out by titration is not the strength of the acid or the actual acidity of the acid. This point you should always remember. So we are titrating and we are finding out. What we are finding out by titration is the total or titrable acidity. It is also called the concentration of the acid solution, but it is not the effective concentration of the acid solution, which is the strength of the acid solution. So now, suppose if you titrate acid and base, you are getting salt and water. And this is called Bronsted neutralization. Why it is called Bronsted neutralization? According to Bronsted and Lowry theory, acid is a proton donor and the base is a proton acceptor. Therefore, a proton comes from the acid and it goes to the base where water is made and the salt comes out. Therefore, it is a transfer of a proton. Therefore, there is no need for formation of the salt. Even water is not required for this reaction. If you take HA as an acid and B as a base, what is formed is BH plus. This BH plus is the conjugate acid, where A minus is the conjugate base. So we are getting a conjugate acid and a conjugate base and the acid and the base. And during this reaction, we are using either an indicator or a pH meter to find out the equivalence point. So we have taken an acid in a beaker and we are titrating it against the base taken in the burette, and I want to find out the equivalence point. That equivalence point can be indicated by the use of an indicator or a pH meter. You look here, when I'm adding NaOH in aliquots, the OH minus and H plus will go on reacting, and water molecule which is present in the solution is slightly ionized. Therefore, the H plus ions are consumed. In order to maintain the equilibrium, a new ionizations are taking place. But during titration, what happens? A buffer is produced. Watch closely. Suppose I am taking acetic acid. So, suppose 100 molecules of acetic acids are present in the beaker. I am introducing just 2 drops of sodium hydroxide. When the sodium hydroxide falls down, the sodium hydroxide takes H plus ion from the water. Now, in order to maintain the equilibrium, CH3COOH gives H plus ion. Now, it becomes CH3COO minus and Na plus. It is a sodium acetate. Now, the system is containing sodium acetate and acetic acid. So, sodium acetate and acetic acid is a buffer. A weak acid and its a salt is a buffer. Now, when the titration goes on, automatically the quantity of the sodium acetate will go on increasing and the concentration of the acetic acid will go on decreasing. Now, you can calculate the pH of the buffer using the Anderson-Hasselbalch equation. Therefore, there will be a condition at which the concentration of the salt and the concentration of the acid will become equal. Therefore, in that point, log value will become 0. Therefore, that point pH will be equal to the pKa value according to Anderson-Hasselbalch equation. Therefore, if you make a curve, so in the x-axis, you have taken the equivalence of OH minus ions added, and in the y-axis, you have taken the pH. Therefore, you are getting a curve like this, where the place where the CH3COOH and CH3COO minus are in an equilibrium, and according to Anderson-Hasselbalch equation, the salt concentration and the acid concentration, they are equal. there will be a small flat portion. Actually, the curve is slowly increasing, and nearing the pKa value, there will be a flat portion. And that flat portion is the portion where the pH is maintained, or it is acting as a good buffer. So that is almost the equivalence point where these concentrations are equal. So this is how the indicators are finalized. You will be choosing an indicator which will work perfectly, or which will change its color abruptly at this pH level. Why in certain titrations phenolphthalein is used, in certain other titrations methyl orange is used, or Congo red is used, or some other indicators are used. These indicators are chosen to work in a particular pH range where the equivalence takes place. Actually, the indicator, before choosing the indicator, you have to draw the pH versus titration curve. Only from the curve, you can come to know the flat portion where the buffering is perfect. Only from that, you can find out which indicator can be chosen. Now look here. So when the half titration relatively flat at a particular point, it is where a good buffering is seen. So if the flat portion is larger, then good buffering is observed. But both the ends of the flat area, the titration curve breaks sharply. There will be a sharp increase or sharp decrease in the titration curve. So the flat zone, that is the buffering regions of the acid and the conjugate base pair. So one can find out the amount of salt to be taken to prepare a better buffer from the curve. You look here, you are taking ammonia and you are titrating it against hydrochloric acid. Therefore, the initial pH is very high, 12, and the final pH is going to be 7. Therefore, it is coming down. There will be a flat portion where the equilibrium between the NH4OH and NH4Cl. See, a weak base, this is its salt. So when this combination is attaining the good buffering region, at that place you can find a flat portion. Suppose if you take a hydrochloric acid and titrate it against NaOH, 80% of NaOH is required to change the pH. So pH change is not very sudden. It is almost acidic. Only when the 80% of NaOH is consumed, there is a sudden increase in the pH. Therefore, the buffering is seen from 1 to 13 almost. So here it has a sharp increase. So the pH change is not very much pronounced. So look here, sometimes we can take the acids with more than 1 pKa value. More than 1 pKa value means you take a phosphoric acid. It has 3 replaceable hydrogen atoms. When one hydrogen ion is replaced, you are getting H2PO4 minus. For this particular equilibrium, the pKa value is 2.24. When another proton is released, you are getting H2PO4 minus in equilibrium with HPO4 2 minus. The pKa value for this equilibrium is 7.20. When one more proton is released, you are getting HPO4 2 minus and PO4 3 minus. For this equilibrium, you are getting the pKa value 12.40. Therefore, 3 pKa values are much separated from each other. Look here, there is a vast separation among them. 2.24, 7.20, 12.40. Therefore, what happens? At around these places, 2.24, 7.20, 12.40, at these places, a flattening of the curve, flattenings of the curve are observed. But above and below these flats, you can see a sharp variation in the pH. So look here, when you plot pH versus the volume of NaOH added, and if you plot it for the phosphoric acid, you are getting a flat region in the pH range 2.24, then it suddenly increases. And again, it attains a flat range in the pH 7.2, and then it increases sharply. And again, it attains a flat region in the 12.4. Therefore, at all these regions where a flat curve is observed, a buffering capacity is seen, but the buffering capacity is very poor because it buffers at three different places, but to a very small extent. Therefore, most of the biological buffers are made up of this phosphate buffers. But if you take a citric acid, the pKa values are very close, 3.1, 4.7, and 6.4. Therefore, almost they are flat from 3.1 to 6.4. Therefore, it is having a relatively flat curve throughout. Therefore, it has a good buffering capacity in a long range of pH. It is able to maintain the pH from 3.1 to 6.4. A long range of pH can be maintained using the citric acid buffer. But a phosphoric acid buffer, it is having a large gap between the pKa values. Therefore, it can maintain pH at different spots, but the buffering capacity is very less in every range. Therefore, citric acid is biologically, which is used as a better buffer, but many of the biological buffers we are using are citric acid buffer or carbonate buffers. So that is about the acids with more than one basicity. So the next one, amphoteric compounds, amphiprotic compounds. Look at this equation. This is cationic, an amino acid where the amino group is ionized. This is a Zwitter ion. Both amino group and acid group are ionized. This is an acid group is ionized, but amino group remains unionized. For the first equilibrium, the pKa value is given number 1. This is pKa 1. For the second equilibrium, this is pKa 2. But the pH is equal to the average of them, pKa 1 plus pKa 2 by 2. Now, from this, we can understand proteins can act as buffers. And also, you should know what is isoelectric point. Isoelectric point is the pH at which the amino acid exists as a Zwitter ion. Now, ionization of amino acid is pH dependent. That is another important point. Ionization of amino acid is pH dependent. And also, amino acid, which is trapped inside the protein. See, protein is a polypeptide chain. Normally, in a long chain, the terminals will be ionized. An amino acid molecule which is trapped in between a protein, a long chain protein, it is non-ionizable. And also, if you look at the 3D, three-dimensional protein structure, it is also pH dependent. So pH even collapse, the change of pH can collapse the three-dimensional protein structure also. I have already explained this, why silk sarees are not washed with soap, because the pH change will collapse the beta pleated sheet structure of the silk fibroin. And also using the shampoo for the head, the hair is made up of protein, and when you change the pH, you have to wash the hair with a neutral pH. When you change the pH, the protein structure will be collapsed. So biological systems are maintaining the pH by a metabolic production of acids like lactic acid and also bases like ammonia. In our body, there is an automatic generation of acids and automatic generation of bases like lactic acid and ammonia. When you are working more, you are feeling tired. That tiredness is due to the synthesis of lactic acid in your body. So lactic acid synthesis is there. And also similarly, when you are eating protein, ammonia is synthesized. Therefore, this metabolic production of lactic acid and ammonia is maintaining the pH of your body in the biological systems. And also in the lungs, there is bicarbonate buffering is taking place. Bicarbonate buffering. Suppose if your lungs becomes acidic, that's all. This corona is somehow, it is affecting the pH of the lungs. So when the pH of the lungs is affected, the surfactants will fail. Therefore, the oxygen intake will be less. Therefore, the blood pH will drop down. Therefore, it involves so much of a complicated processes. But in the lungs, the pH is maintained because of a bicarbonate buffering. That is H2CO3 in equilibrium with HCO3 minus. How much of bicarbonate is there? How much of HCO3 minus ions are there? And depending upon their quantity, the lungs pH is maintained. Lungs should never become acidic. So the biological systems, the pH buffering is taking place with bicarbonate buffering or phosphate buffering or proteinate salt buffering. So these are all the various bufferings taking place in the lungs or in all other parts of the body to maintain the pH of the blood. And if you take the blood, venous blood, that means the blood running in the veins. See, our whole biological system has blood vessels. Certain vessels are called veins. Veins are found on the outer side, whereas arteries are found in the inner side. They are very deep within. Arteries, they take the oxygenated blood from heart to other parts of the body, whereas veins, they carry the deoxygenated blood from various other parts of the body to the heart. If you measure the pH of the blood in the veins, it is between 7.36 to 7.40. But if you take the blood from the artery and measure the pH 7.38, and it is in the range 7.38 to 7.42. It is because of the oxygenation and deoxygenation. But there should not be an abrupt change in the pH of the blood, which will be fatal in effect. Therefore, our body, the blood pH, the pH in the lungs, the pH in the mouth, the pH in the stomach, and the pH in the liver, and the pH in the brain, all these things are maintaining the pH by adjusting the equilibrium in the bicarbonate buffer or phosphate buffer or proteinate buffer. So these buffers are automatically working in our body to maintain the pH. So that is the biological importance of the buffer. So oxygenated blood, you can see the myoglobin also. See, hemoglobin is oxygen carrier, where myoglobin is oxygen storer. Suppose if you go to the mutton stall, you can see the oxygenated myoglobin, the fresh meat and the old meat, there will be color difference. This color difference is because of the myoglobin getting deoxygenated. So oxygenated myoglobin color and deoxygenated myoglobin color. Oxygenated hemoglobin, deoxygenated hemoglobin. These are all various buffers working in our body. See, you should breathe well first of all. You should breathe fresh air, and the myoglobin in our body should be well oxygenated because they are oxygen storers. Whereas hemoglobin is an oxygen transporter. If you are anemic, if you are deficient of iron, then the oxygen carrying capacity of your blood will drop down. Oxygen will not be well supplied to other parts of the body. Therefore, you should always maintain your HP level. Hemoglobin level has to be maintained. And if you are having sufficient hemoglobin, sufficient iron in your blood, then the oxygen supply will be good. Otherwise, you will be drowsy, you will feel sleepy, and you will feel tired always. Therefore, you should eat well to maintain the hemoglobin level or the iron level of your blood. Therefore, the maintenance of the pH is very important. So drinking water, breathing well, the breathing exercises, they are all very important to maintain the pH of various parts of our body. So breathe well, and you are all in the lockdown time, and you are all in-house, do some exercise, do breathe well at least, sit in a place calmly and inhale and exhale with a full consciousness so that more amount of oxygen, the lungs expansion will be very effective. So oxygenated blood, deoxygenated blood, and the venous blood, arterial blood, everything I have told you. And look at this. I think with this, we are coming to the end of biophysical chemistry. So I have completed biophysical chemistry also. So we have seen plenty. So with this, I complete 2 units in the physical chemistry 2. I have already completed group theory, and now I have completed biophysical chemistry also. So if you have any doubt, you can ask me.